Hello, good morning, good evening, ladies and gentlemen. My name is Kourosh, and um, I'm here to present an overview on the on-bottom stability software version 4. And I hope we will have a good time together in the next round about an hour time. I have my colleagues Nick, who would help me navigating through the slides. So we may just get it started. Nick, can we go next? Excellent. So what I would be covering is to provide an overview on the PRCI OBS software and what is happening in version 4 upgrades. We would go over some popular technical topics that most users have been asking questions in those regards. And also we go over some further conducted research. And towards the end, we would have a little bit of basically demo on the software. Next, please. Excellent. So the PRCI software is the industry-leading software for on-bottom stability analysis for submarine pipelines. And it came about as a result of a series of research conducted as a JIP between American Gas Association and other parties, including PRCI itself. The research included laboratory model testing for further understanding of hydrodynamic forces on the pipelines. Also, there was a separate testing for better understanding of the pipe-soil interaction. That was the first ever testing that was conducted. As the result of the research, went into a series of guidelines for stability and also development of a software. The program consists of 3 main parts when it was originally developed. They are known as level 1, 2, and 3. And as the level number goes up, the complexity level increases. We will get into that in continuation of the presentation. Next one, please. Right. So let's look at the problem of stability, pipeline stability on the seabed, and what the OBS software does for this. So the pipeline resting on the seabed is exposed to the forces coming from the waves and the current. The waves will apply often oscillatory forces, where the steady currents apply unidirectional forces. As the pipe is in contact with the soil underneath, then there is a soil friction that resists the movement of the pipe against those hydrodynamic forces. Traditionally, there has been a simplified method using Morrison equations to assess hydrodynamic forces, and also a simple Coulomb friction to assess the frictional forces. This research that we just talked about started looking into further understanding of these hydrodynamic forces and the soil models. Can we have a click, please? Yeah, so the 2 key is hydrodynamic model test and force model, and another click is the pipe soil interaction initial model for sand and clay was developed as a result of this research. Next. Okay, so next. And next. Excellent. So the 2 parts of the research, they came together and they developed a 3D dynamic analysis model, which we now call level 3. And that was to model a length of the pipe that basically a finite element model of that pipe length, which is exposed to hydrodynamics and soil interaction, which basically the pipe embedment will get updated in a timely manner. So the model gets integrated over time. Whereas on the level 1, the hydrodynamic model test results helped with better prediction of the drag and lift forces. Next. And next, please. Excellent. So what happened was that once they developed the level 3, they realized that running this level is very time consuming and impractical for some real projects at the time, because we're talking 1980s and early 90s, where the hardware of the computers, they were not that strong and the memory was extremely expensive. So they thought that all this great research that they've done and they've compiled it and implemented into this 3D, how could they use that in a more efficient way? Next, please. So then there was the idea of having a quasi-dynamic or quasi-static, could call it both, a model which is not as time-consuming and intensive as level 3. So they called it level 2, and that we get in a minute into what that is and what is the difference between this and that. Obviously, the level 2 performs a two-dimensional analysis, so it takes away the finite element, but also it approaches the hydrodynamic forces from a statistical point of view rather than a time domain simulation. Another parties involved in this research, they went ahead and in a different direction. So they did a lot of thousands and thousands of 3D simulations, and they applied a series of regressions, and based on those regressions, they developed basically a method which is now called generalized method. So the generalized methods uses those thousands of time domain simulations which use single node, and based on that they developed a methodology to predict the pipe embedment and the pipe weight that's required to be stable. That is now captured in DNV F109. Next one, please. As I mentioned, so a statistical approach to prediction of the embedment, advanced force model, PSI was included, and fast and quick solutions. So that became a very popular solution to the whole problem. Next one, please. Excellent. So let's have a 20 plus 5 years around that time lapse where the software has become the industry leading software for pipeline stability, and it's been widely used in Gulf of Mexico and parts of Europe and the Middle East as well. Then users have started different experiences with that. There was found, especially level 2 being most frequently used, they found a bug in there, and also the original spectrum was Ochi-Hubble, which then they moved on to John Swab spectrum, became more popular, which was not in there. There was some boundary layer limitation there. In the soil area where they originally developed the pipe soil interaction model, they had limited data, where after developing those models, there were more tests conducted and the data became even more available. Also, they realized that the level 1 is too simplistic and cannot provide satisfactory results for the recent advancement in the computers, and computing then the level 1 became very unattractive. So therefore a series of scopes and the requirements came up for this software to keep it up to date and to keep it as the industry leading software. Uh, in addition to these technical items, the user interface was getting very outdated, and it was getting impossible to load the software onto the modern computers. So those things resulted in a series of research work that Worley and Intexi in particular have been involved in making those changes and evolving the software to a modern one. Next one, please. So the upgrades, there is general additions. A few enters, please. Nick, thank you. Excellent. So we've rewritten the user interface, which later today, if I had a chance to show you the live demo, then we would see the web app version of it. So far as a user, you've access to desktop, but a new upgrade over the desktop is that technical toolboxes have done a tremendously good job in replicating the desktop on the hub, which is very easy to use. And it's probably going through some beta versions and slowly becoming available to the users. One of the things that in the desktop as well as in the web application version, there is a bit of database where you could store your cases, and we've used some modern features there. There has been a lot of additions to that, and some of the hard-coded parameters that were in the actual Fortran 77 code, they are now user inputs, and it gives flexibility. There has been added some input data sanity check that would help ruling out trivial mistakes like putting negative numbers or letters and things like that. Next one, please. Some plotting features have been added as well, and at least upgraded, that the users can save those plots in the PNG form and directly can go into their reports. Next, please. I would, as a user, you might have seen a list of improvements, but I thought it's still worthwhile quickly listing them. So in the level 1, it's been logarithmic boundary layer formulation added, and also the marine growth option has been added. The absolute stability method based on the DNV F109 was from the users' feedback that they wanted that to be included in there, which is now a new module there. Next one, please. At the level 2, again, logarithmic boundary layer formulation, marine growth specification, John Swap, and there was 2 new models, soil models, the popular soil models, which are still based on the original soil models that were in the software, Valley and Lawn for clay, and Valley and Softberg for the sand. There was a bug for the current dominated situations, and that has been removed from the version 3. So most of the results, if there is a current involved when you compare it with version 3, you would have difficulties comparing because the old version would not produce correct results. And also there has been some parametric run functionality that has been added to the software, which we'll get to that later. So next, please. The level 3 we've had small changes to the level 3. We've kept it as legacy. One of the reasons is that these days design houses, they have their own dynamic simulator based on the modern finite element packages. but we still use the level 3 as a legacy um, for stability analysis, not combined with buckling and things like that, but just the stability for stability analysis purposes. Similar changes: logarithmic boundary layer, Jones swab spectrum, being able to run multiple wave seeds, and plotting, additional plotting features. And now one of the good things at level 3 is that you can run many seeds, and you can specify the seed numbers. It wouldn't necessarily generate it automatically. If you want to do sensitivity analysis, you can choose to have exactly the same seed number. If you want to change other parameters and see the effect, you will get exactly the same storm applied to your pipeline if you want to do sensitivity on other parameters. Next one, please. Right, so hopefully this slide would put the changes in a bit a better perspective. So in the horizontal direction, we have level 1, and then DNV F109, level 2, level 3, and then these gray boxes, which are the research and additions that are not in the commercial copy just yet, but it is available at beta version and is being reviewed by the project team and PRCI members. So from the left to right, the level of complexity increases. And we've gone beyond the level 3 in the sense that we've looked at shallow water calculations. How do we predict the water kinematics in a simplistic way in shallow waters where the wave breaking zone is? We've done one phase of it, and we'll show some of the results later. On bottom kinematics, one of the things that users have always wanted is to be able to get on bottom kinematics around the pipe, as well as hydrodynamic forces on the pipe nodes, such that they can use it in their own dynamic simulator. The current limitation that is coming from version 3 is that the number of pipe nodes are restricted to 101 nodes, and they must be equally spaced. And this addition, which we've just called it on bottom kinematics, it includes forces as well. You can arbitrarily define the length of the pipe and arbitrarily define the spacing between the nodes, and the software will export time series of on bottom velocities, accelerations, and drag and lift forces that can be used with your in-house simulator. The next one, which is nodal dynamic simulator. One back, a couple of more words there. Excellent, thank you. So the nodal dynamic simulator is similar to level 3, except that instead of having a length of pipe, we only have one pipe node, and we do the time domain simulation for one pipe node. So that's not nice to notice. The last one is the API deployment. Basically, most of these functionalities, we have converted them into the API format, and it can be utilized in such a way, such a very versatile way. You can embed it in your own workflow. Next one, please. Okay, so because I wasn't sure the audience if everyone is familiar with API, the API intends to provide flexibility to the users, use the program modules in their larger workflow, and perform customized parametric study the way they actually want to do it, access more intermediate results, not just the end results, but choose to have more intermediate results to be able to do more due diligence. The APIs are often more suitable for advanced users where they can do some scripting with Python. Now, we we had a little bit of technical problem today. I meant to be the presenter such that I could use my computer, but we had to give up on that. So I have prepared a small demo here to show the API, and unfortunately, the way it's going, I wasn't able to be a presenter because of some restrictions on the computers, I suppose. So we might skip this and move on to the next slide. Okay, so this is just a wrap up of the history of the software, the changes that we've done, and sometimes the genesis of the changes or where they come from, what was the motivations. And there is a relatively long list of additions to be done on the software in different areas, such as cable analysis, such as all other areas. But that would be discussed in a separate probably session. But for now, I thought we can present some of the technical matters. Hopefully, it would be exciting for the pipeline engineers that are attending tonight. Next slide, please. Right. So, in particular, level 2, when we look at the methodology, the stability analysis is done in two main steps. Step one is an estimate of pipe embedment and soil passive resistance are obtained. So the first step is done this way, and this estimate is done at the end of 4-hour storm buildup and during the design storm at these two steps. Imagine if the sea start becoming rough and then there is a storm, the significant height start going up and is predicted to be 4 hours it would be fully developed, such that the significant velocity at the bottom reaches its steady. So at the end of 4 hours, where you can see on the chart, is one assessment, and during the horizontal plateau where the US is reached this stability, there is another assessment. At this point, then after you know that, then you go and do a stability analysis check, absolute stability check, if the pipe is going to be staying there during the storm. And with having those additional passive resistance, we expose the pipe to these 4 waves such that we assess how these forces are acting upon each other, or whether the pipe is going to be stable or not. Next one, please. Excellent. So I just give a heads up to Nick, that is my colleague, that because of not being able to do the live demo, they might use part of the time for the demo to further explain these technical matters. Or if you wanted to interrupt me later and there is someone at your office who could run a quick demo, I would be happy to do that way as well.
I think that's fine, Kourosh.
So this is the overall workflow of the level 2 methodology. If we click once, as we see the input from the top, the input data starts coming in, and then we go wave height spectrum transform to the bottom velocity, and then goes to the right side where we get AGA force module, and then we go to a build up sea state model for the 200 waves, or the largest 200 oscillations. This is the 4 hours ramp up estimation. If you click once, Nick, please. Excellent. And another one. Yeah, so this, excellent, that's good. So this green box here is showing the 4 hours storm buildup, and the following is the 3 hours. At the end of 4 hours, which is done in the green box, the soil resistance and embedment is recorded, and at the end of 3 hours also recorded, and they are fed into the stability checkbox. And also the AGA force module is available when we need to calculate hydrodynamic forces. So that's the actual workflow of the level 2. The PSI model, the way it works, if the hydrodynamic forces are large enough to move the pipe uh, between 0.02 diameter and half a diameter, it's where the embedment starts increasing, and it goes through a cyclic basically movement according to how many waves we are applying, and then the embedment gets updated. Next one, please. Next one, please. Maybe back 3 slides. We went a bit too fast. Excellent, that would be it. One more. Can we forward one slide, please? Excellent. So if we look at the manual of the software, when we're talking the ramp up, there is 5 waves that are applied. The 200 waves, we apply these coefficients to the US and incrementally increasing that factor to 1.36. So one of the research items that we did was to evaluate and validate these numbers to understand where these numbers come from. So what we did extreme value analysis and compared the results against the those charts provided in the manual, and we realized that the calculations was done in the 80s was really accurate, and there would have been probably mathematicians looking into these problems. So we found that those green parameters, factors, they are indicating, the highest 100, the highest 50, and the highest 12, and so on. And 1.36 is the highest, is the maximum waves that can happen at the tail of the ramp up around this area. Next slide, please. And this is for the storm. Again, the top left frame is from the manual, and on the right hand side is where our work shows that these coefficients that are multiplied to US, they are validated against extreme value analysis methodology. Details of these discussions are in a paper, in the OMA paper in 2018, and you can find the formulation and the descriptions in this regard. Next one, please. So this is showing the bug that has been removed. Previously, the current was treated as a wave in the version 3 of the software, and it would predict additional embedment, which was not realistic. And if you go next slide, please. So this shows the results. The blue line is after bug fix, where the red is the original code. In the current only and wave only and wave and current, the left column shows that the blue stops after 5 oscillations, which is showing the how the software calculates the initial embedment, whereas the original code, although it's current only, the original code keeps going up, whereas the new code stays at the constant. The wave only, the two results are identical because if there is no current, then the bug is not invoked. But when there is a wave and current, and the current is significant, then we could see that the red color keeps oscillating for all the 9 waves, whereas the blue stops here, and at the 9th wave only it goes up, as shown in the oscillation part over here. Thank you. Next one, please. And this is once we added Velian Sotberg and Velian Land clay. These are some intermediate data that has been plotted. We ran 6 cases in this case and compared how the embedment changes when we change the submerged weight of the pipe. So as the submerged weight increases, we see that initially the embedment is increased, and different waves apply different level of addition to the embedment. In the first row and then the bottom row from left to right, we notice that the embedment starts decreasing because the pipe gets, especially for the sand, the pipe gets too heavy and the waves are not able to move the pipe. The pipe gets heavy and sink initially more because it's heavier, but it cannot be oscillated because of the waves, because the waves are the same, but the pipe is too heavy, and therefore the embedment is not increased, although the pipe the pipe weight is increased. Next one, please. Moving forward, yeah, and that shows the embedment and horizontal factor of safety. You can follow the how the submerged weight increases. The lightest one immediately start having added embedment, and then at 200 cycles onwards we get a steady, whereas the heaviest pipe, which is a double dot dash line, is almost constant. So the embedment stays at its original value, which is bigger than the other initial embedments. And on the horizontal factor of safety, as SG increases, we naturally get more factor of safety, but at about past 1.8, we start seeing adverse effect on the horizontal factor of safety, for the same reason, because if the embedment is not increasing, we're not benefiting from the shielding effect that the embedment provides. And therefore, apparently there is a small reduction in the factor of safety. We had a couple of users having these questions that despite they increase their wall thickness or concrete thickness, they don't see improvement in the factor of safety, and that's because sometimes your pipe is too heavy for your environmental conditions. And next one, please. Right, so this is again a parametric study on the soils. I skipped describing these parameters. Move on, please. Next one. So the left plots show the Velian Sotberg for sand, and the right-hand side plots shows the PRCI original. And what it is the maximum breakout force predicted by the soil models. And if you read the axis, you've got Casey, Culligan coupling number, and also we've got the other axis, the submerged weight. Whereas on the original soil model, we have Casey and we have relative density. By looking at these plots, you realize that the Velian Sotberg model produce a lot more consistent behavior at the for the breakout forces compared to the original sand, which then is an indication that Verley and Softberg has a better backup test data compared to the original soil model. Next one. And this is the showing in a color map showing the difference between PRCI and Verley and Softberg percentage-wise. You see that the difference which is around 0 is where you get the relative density to be around 0.5. So for the original soil, if the relative density is set around 0.5, we get the minimum differences between the old and the new soil models. But we could see in some cases we get a really large difference in the predictions of this breakout forces. And this soil model selection validation is still a hot topic, and we are still working on that topic as well. Thanks. So next slide, please, Nick. This is the same plots just for a different soil, which is a clay. For the argument's sake, I'll skip this plot as well, just to save some time. And again, you could see the differences in the clay is much less than the differences in the sand. The differences are where the SU, the shear strength is around midpoint. We get closest results between the two old and the new models. Thank you. Next one. Yeah, so these research that I'm trying to show you in the next few slides is showing the work that we have done and soon to become part of the software. Please move on. So the original model, hydrodynamic model, that was a model test that was done for PRCI is in this box here. Because of the physical testing rig limitations, they kept the Kc under 100 and the alpha under 1.5. So we did an extensive work with the CFD and the supercomputer and expanded the data that we have to the green box. So where we could increase the Kc to 500 and also the alpha, which is the current to wave ratio, to 2. These particularly high Kc numbers are very helpful for the small diameter pipes, such as cables, such as 6-inch pipes, MEC lines, and all that, which would provide us a lot of insights. These plots here show that how the DNN, which is a machine learning methodology, has been used to predict the intermediate values, where we did between these dots, which are the actual simulations, how do we get the intermediate points for lift and drag coefficients. So next one, please. The other challenge was shallow water, which we have done phase 1. It was originally known to be a large scope. We developed a methodology such that any generic site, if we don't have any information when we are at the feed level or concept level, which the operators don't want to necessarily spend millions and go in the field and get the actual data, how do we have a prediction of those areas? We set up a constant slope. And next one, please. And we sort of started at, say, 25, 27 meter water depth, and then coming back to the shore and following the sea spectrum and see how that changes. We use the software called Mike, which is a DHI software, very popularly used for coastal engineering. And we did it for a small range of wave heights and we calibrated the results, and we created a machine learning model that if you plug in the spectrum at the deeper end, you can choose at the shallow end what would be the kinematics at the bottom. So next one, please. I guess that's showing some of the spectrums. As we go in shallow water, we get different between Fenton, linear, and Stokes. When we go into deeper water, they seem to be matching better together. So this work is yet to be completed for large wave heights, and that would require large simulations for sure. Next one, please. Yeah, that's the last slide for me, and that is the grouping the research and the strategic advancement of the software. There's always needed more technical research and modeling. There is always we need to expand the features of the software, such as the APIs that we've done, and more so with what Technical Toolbox has put together as a hub, which I'm very, very sorry that I couldn't show that to you tonight. That was one of my favorite ones, and I had prepared really exotic examples. The software development itself, we're jointly doing the back end, and Technical Toolbox is doing the front end, and also they are looking after you from a licensing point of view. So that sums up my talk for tonight. Please, if there is any question, or I can give it back to Judith or Nick.
Yep. So if there are any questions, there is a chat box on the right-hand side. I do just want to add, Kourosh, we'll go ahead and record the demo that you had intended to give here, hopefully later this week. And so everyone in attendance tonight, you will still get the demo that Kourosh was going to show. It'll just be a day or two later, and we can answer follow-up questions on the software from there. So if there are questions, there's a chat box on the right-hand side. Go ahead and put them in, and I will read them out loud for Kourosh.
Microphone, speaker. If anybody talking, I'm afraid I cannot hear.
Kourosh, I'll read the questions out loud, and you can just hopefully answer live. So the first question here is, currently AGA is deployed to cover a flat seabed, but there's potential for future adaptation to accommodate a seabed with a cross slope.
Okay, just one moment. I will switch my speaker. Okay, could you please repeat the question, Nick?
Yes, it is. Currently, AGA is deployed to cover a flat seabed, but there is potential for future adaptation to accommodate a seabed with a cross slope.
This is a good question. If we basically leverage on the advanced FEA packages, such as Abacus or ANSYS, not just for seabed modeling, but rather including the internal pressure and temperature, we think leveraging on those would be the best way to model a realistic seabed, and that would basically it would be for us to reinvent the wheel if we want to incorporate it into the OBS. So what we are trying to do, we are trying to make it possible for the users to take as much information as needed out to the to those generic packages, software packages, and they utilize those. In that sense, then it is, yes, it has been thought of, and this is how we are perceiving it now, but we are open to ideas. Yeah, especially for cables and things like that that are flexible. we can think of, we have thought about the OrcaFlex as one example, or Abacus as the other one.
Okay. Next question. Is it possible to obtain the precise value of concrete thickness necessary for ensuring pipeline stability rather than opting for a range with incremental measurements? This would eliminate the challenge of accurately determining the exact value within the range.
Yes, it is possible to apply the exact value in the software. If you don't want to go through a loop, then you can just put exactly what you want and put the initial and the end value to be the same value, and it will calculate it.
Okay. Next question. Some inputs, such as wall thickness, have a limitations in terms of range with a maximum limit of 50 millimeters. Is it possible to extend this range further?
Yes, definitely. It is possible. We did not think that it would be popular to have more than 50 millimeters of wall thickness, but maybe there are special cases of very deep, sort of very thick pipes. If you find it a limit, then it is very easy to remove that restriction and increase that wall thickness for sure.
Okay. Another question: has the PRCI level 2 or 3 of OBS been compared with the DNV generalized method? And if so, which one gives less conservative results in terms of thinner concrete thickness?
A few years ago, we did this attempt, and we tried to do that. We realized that there is a significant number of intermediate assumptions and parameters there, which makes it difficult to compare apple to apple. So we went ahead to some extent, and then we realized it would not be fair to make it a judgment and a conclusion about which one does more conservative or less conservative. If we strictly follow the F109, there are different safety factors implemented, amplifying factors for safety classes, all these different things, geographical locations, and there is quite a number of things that is, whereas in the OBS, you're dealing with bare forces and the ratio of them, and not so much of those basically safety classes involved, or other parameters as well. So it would still be an interesting exercise if someone wants to do it for their project, and we would love to hear about that, but we don't have a definite answer for that.
Okay. Is there an option in this new version of software to include multi-directional environmental, that's wave and current parameters, instead of only omnidirectionality?
So there is, if you follow the version 3, you could have mixing of two sea states coming at different angles. And then there would be a mixing factor that was there and is still there, say, half of this of half of that. This is the level that is at the moment. And you can have a spreading function, but having multi-directional more than 2, we haven't thought about it. Or it's not hasn't been in the priority list. But as I said earlier, depending on the applications, if we receive a couple of paragraphs, we would seriously take that into account. To me, as long as the mathematics behind it is clear, which is clear, it's as a matter of implementing it. So it doesn't need research component. It's more of implementation type of task. So it is doable.
Okay. Next question. In certain case studies, it is necessary to assume zero embedment, which results in the absence of passive soil resistance force for conservatism. However, during absolute stability analysis, an embedment of 0 millimeters cannot be assumed. It would be automatically calculated in accordance with DNV guidelines. Will it be possible to have the option to assume it is the same as we have for level 2?
If I digested the question well, in our software, in the OBS, the question was that it always calculates the embedment, but sometimes we don't want to. And how do we use the software and such that it will not apply the embedment? If that's the question, yes, it is possible. If you just put, instead of putting 0 in the embedment, at level 2 we're talking, if you put 1 millimeters, then the wave forces will bypass, the embedment will not be predicted. Or you could put something non-zero, any small value, the program will bypass the embedment calculation. So could we double check if I have answered the question?
Yeah, Khalifa, if that answered it correctly, looks like he's got a follow-on question, Kourosh. So we'll follow up with separately.
Sure.
Next question, probably the last question actually. Is there wave modeling for different wave depths in a single parametric run?
For different wave depths, as in we change the water depth?
That is how I'm reading it, yep.
Okay, so yes, let's say we are having undulation on the seabed and the sea state on the surface is the same, but you get different points along your pipeline to have different depths. Yes, at level 2, you can exactly do that by selecting the water depth range. There is very soon is going to be the parametric study component that's going to come out, and you can specifically say, I want it at 100 meter, 110 meter water depth, and 130, 150. You can exactly give your water depths, and the program calculates the on-bottom kinematics and forces for those exact water depths.
Very good. Okay, well, we wanted to thank you all for attending today. Just to reiterate, so later this week, you will receive a copy of this recording, and you will also receive a separate demo of the OBS software as well, all the items we didn't show today. So you'll have both those later this week. If you have additional questions, you can, of course, reach out to us at technicaltoolboxes.com, and we will direct them accordingly. But thank you again for your attendance and your great questions. Have a great day.
Thank you, everyone, and thank you, Nick.